Hello everyone, this is continuation of our series on current electricity where we discussed Ohm's law and also resistance and the parameters affecting resistance, right? So let's start with a topic called drift velocity. Drift velocity and relaxation time. So these terms might be new to you, but let's understand what happens. So let's say this is a conductor, right? This is a conductor. So when there is no potential, no electric field applied to this conductor, there will be electrons which will be in random motion, right? They'll be colliding around with each other. There will be multiple collisions, but let's say there are an electrons v1 v2 v3 with different velocities, right? But overall the average velocity will be zero. The average velocity of all these conductors will be zero in absence of any potential or electric field, right? But once we apply electric field here, once we apply electric field, these conductors will get energized, right? These will start vibrating more. These will start collision with nearby ions or atoms, right? And they will start moving in a particular direction, right? So relaxation time is basically the time between two successive collisions, right? So an electron, let's say an electron will be in vicinity of some atoms, right? So between two successive collisions, the time average time is relaxation time. So it will, once we apply an electric field, it will collide with the nearby atom for some time, and some electron may collide for more than relaxation time, and some may collide for less than relaxation time. So the average time of collision with successive collision is relaxation time, right? Now let's talk what is drift velocity. So relaxation time is indicated by tau, and drift velocity is indicated by Vd, V with a D. So now let's say that we apply electric field, right, in this conductor. So now conductors, electrons inside this conductor will get a velocity, right? The sum average velocity will no more be zero. Average velocity will no more be zero. So the average velocity of electrons in presence of external field or potential is nothing but drift velocity. The average velocity in presence of field or potential is drift velocity, right? So if we talk about one electron, right? If we talk about one electron, what will be the acceleration in presence of electric field? Acceleration is force by mass. So force to an electron is minus E into E by M. Minus sign means electrons are negatively charged and force is opposite, right? Force is attractive. So EA is minus EE by M, right? This is the acceleration. Now, you know the relation between VU, A and T, right? So let's say V equal to U plus AT is what we know. V equal to U plus AT is what we know. Initial velocity, as we discussed, initial average velocity when there is no field and all that is zero, right? So this term is zero, right? So velocity is nothing but minus EE by M into tau. Velocity is minus EE by M into tau. Now, so why I have written T tau here instead of T? Tau is the relaxation time. So now we are talking about successive collisions, right? Average time, and hence this velocity becomes average velocity. So this is the expression for drift velocity. So drift velocity is average velocity of an electron in presence of an electric field or potential. Now let's talk about one more term. What is the relation between this velocity and the current? We are talking about current, right? Current electricity. So let's say this is the conductor we have, right? This is the conductor. We have applied an electric field, let's say E, and this is the area. This is the area. The electrons will flow opposite to this field, right? You know, electrons will flow opposite to the field. So the number of electrons which will flow through this area, let's say in delta t time, right? In delta t time will be what? If I is the current, if I is the current flowing, so the number of charge carriers which will flow in delta t times. So charge is nothing but I times current, because I equal to q by t. So I times of current. But if I represent this in terms of number of carriers, let's say n is the number density of electrons, right? Of electrons. A is the area of cross section. Vd is the drift velocity, right? Now, n is the number density of electron, which means number of carriers per unit volume, right? So, charge flowing through this area A in delta t time will be what? Will be Ne, which is charge per unit volume, and now into A into delta T multiplied by Vd, right? So charge per unit volume into the volume and into the velocity is what? The number of charge carriers which will flow in delta T time, right? Now from here you can see that I becomes what? I is N E A V D, right? And we know that Vd equal to E by m into tau. If I talk about the magnitude, E by m into tau. So if I place it here, so I becomes what? I becomes NEA into E by m into tau, right? Which is Ne square by m A E tau, right? This is a relation between current and drift velocity. This one, this is the relation, and finally we have put the expression for drift velocity also. Now you see how current is depending on the parameters like relaxation time when other parameters are constant, right? If I assume n as constant, e as constant, m as constant, you see it is proportional here. Now you see there is a quantity called current density, which is I by a. We have discussed current density is a vector quantity, current is a scalar quantity. So I by a, which makes this term as Ne square by m into tau, right? Ne square by m into tau and into e, right? And this term Ne square by m into tau is written as sigma and into e. Sigma is nothing but conductivity. Conductivity. So this is another expression of Ohm's law. J equal to sigma into E, which we had discussed in the last class also. So J equal to sigma is another representation of Ohm's law, where sigma is nothing but Ne square by m into tau, right? Okay. Now let's discuss about a term called mobility. Mobility. So you know, conduction in metal or any conductor, wire, anything is because of electrons, right? You know, the protons and all are residing inside nucleus, and electron is only responsible for conduction. Similar to that, if you talk about electrolytes, right? The conduction is because of ions. There it can be positive as well as negative ions, right? So to measure this conduction, to measure this conductivity, we have a parameter called mobility, right? So mobility is basically defined, it is represented by mu, and it is defined by drift velocity per unit electric field. So if you apply some electric field, how mobile is your species, how fast it is moving, is represented by this term called mobility, right? So drift velocity is Vd, if I talk magnitude, and E. So you know Vd is E by m into tau. Sorry, E by m into tau, right? So mu becomes E by m into tau by E, which becomes E tau by m. So mu equal to E into tau by m. This is mobility, right? You see, mobility depending on the charge of that species, mass of that species. In case of electron, this will be charge of electron, mass of electron. Tau is the relaxation time, right? Which is also a constant, the time between successive collisions, the average time for a specific conductor, right? So this is how we calculate mobility, right? Okay. And what is the SI unit of mobility? SI unit of mobility will be meter per second, meter square per volt second, right? You can calculate this using this. E is nothing but volt per meter and velocity is meter per second, so meter square per volt second, right? Now let's discuss, we have discussed all these parameters, drift velocity, relaxation time, mobility, and we also know Ohm's law, right? We also know Ohm's law. Now discuss limitations of Ohm's law. Limitations of Ohm's law. So before discussing limitations of Ohm's law, we can discuss this as a subset of one more topic, classification of conductor based on Ohm's law, right? Or conductor, leave this conductor word, classification of material based on Ohm's law. So one type of material is called ohmic, right? And other type of material is non-ohmic, right? So ohmic conductor and non-ohmic conductor, right? So as the name suggests, something which follows Ohm's law is a ohmic conductor. What is Ohm's law? Ohm's law states that potential current flowing through any conductor is proportional to potential difference only when the other conditions are maintained constant, like temperature and pressure, right? So if potential difference and current, they are proportional to each other, then the conductor is said to be following Ohm's law, and this will be a ohmic conductor. But there are some conductors or some conducting devices which ceases to follow the Ohm's law, right? Which ceases to follow this linear relationship, and that's when it comes into the classification of non-ohmic conductors, right? The best example is diode. You would have come across this term, diodes, semiconductor diodes, right? So if you see a VI curve for a diode, so VI curve for a diode looks like this. It won't start at origin, it will start at some point, then it will go like this exponentially. Even if you back, if you see, it comes like this. A sharp turn is here, a sharp steep increase is there. So you see, this is actually not a linear relation between I and V, right? And hence, it is a non-ohmic material, right? Even IV relation for other conductors like gallium arsenide and things, you see that it is something like this. And this type of nature, IV nature for GAS, this is also not following Ohm's law, right? So a lot of devices, practically conductors, follows Ohm's law, but then there are devices, semiconductor devices, and even some metals which ceases to follow Ohm's law, sometimes in normal conditions, sometimes in specific conditions, right? Okay. So next topic is variation of resistivity with temperature. Rho, which is resistivity with temperature. So before dealing this, we already studied in brief how resistance depends on temperature. Like if you increase temperature for conductors, the resistance also increases. But for semiconductor, it was not the case. We discussed that. Now, you know, conductivity is what? Conductivity is given by Ne square by m into tau. We just derived it, right? Resistivity is nothing but 1 by conductivity. So this becomes m by Ne square into tau, right? M by Ne square into tau. Now, let's discuss how this resistivity is depending on temperature. Then we will derive an expression and all that. So this resistivity is depending on mass, charge of electron, and in tau. Mass and charge are constant, right? So if I remove everything, I would say that this resistivity will depend on n into tau. N is the number density. Charge tau is the relaxation time. So if I talk about conductor, as temperature increases for a conductor, what happens is this number of collisions, right? Number of collisions becomes faster. The vibration becomes faster, the number of collisions becomes faster, and time between successive collision will be smaller, and tau will be small, and hence rho will increase significantly. In case of conductors, as we increase temperature, so if temperature will increase, so let's discuss for conductor case. If temperature will increase, vibration will increase, time successive collisions time will reduce, and hence rho will increase. What about n? So n, number density. Temperature does not affect number density a lot in case of electrons, right? Because we already know that electrons which are free will be available for conduction, not much bothered about the temperature in case of conductors, right? So we can say that for conductor, as we increase temperature, resistivity will increase. This is the reason because of which it is happening. Now, if I talk about semiconductor case, if I talk about semiconductor case, so in semiconductor, as we increase temperature, so in semiconductor, charge carriers are not always available. The breaking and coming up of charge carriers is dependent on temperature. So as we increase temperature, my n will shoot out, my n will shoot out very highly, and lot of charge carriers will start coming up, and n will increase, and hence rho will go down. If temperature increases, n will increase, and hence rho will go down, resistivity will go down. And that's why these semiconductors have a special nature, that if temperature increases, their resistivity goes down, right? So they can be used in a variety of applications. And again here, tau does not have a much effect with respect to temperature in case of semiconductor, since we are not bothered about much about the effective collisions, right? Now let's derive the expressions, or not just expression, but let's understand that if temperature equal to T1 and resistivity equal to rho 1, temperature, and then if temperature equal to T2 and resistivity equal to rho 2, so rho 2 will be given by rho 1 into 1 plus alpha T2 minus T1, and this alpha is called as temperature coefficient for resistivity, and this is positive for conductors, and this is negative for semiconductor. So now you can appreciate that as temperature increases for conductor, the resistivity will increase, but for semiconductor, since this alpha is negative, the resistivity will come down, right? So if I plot resistivity versus temperature for conductors, they will actually look like this. They will look like this. This is kind of ideal scenario, but they will increase always. For some very good conductors, they may even increase like this, right? But for semiconductors, it will have a decreasing nature. Rho versus T will have a decreasing nature, and this is we have as a approximate equation to say the relation between resistivity and temperature, right? So let's discuss a very important term now called as electrical energy, and also we'll discuss power, right? So whenever any current flows through any wire, you see the wire gets heated, or you see any appliance which is used for a long time, you see it getting heated. So what is the reason of that heat, and who's supplying that heat? You should know that, right? So let's say this is a conductor. Let's say this is a conductor. AB is a conductor, right? AB is a conductor, and potential at A is VA and potential at B is VB. For a current I to flow, from A to B, what is the condition? VA should be greater than VB, then only I will flow, right? Now, what is potential energy at A? What is potential energy at A, right? If Q is the charge, right? If Q is the charge which is flowing from A to B, so potential energy at A, let's say UA, will be what? Q into VA, right? Q into VA. And potential energy at B will be what? Q into VB, right? Q into VB, right? And what is amount of charge which is flowing in delta t time? That is I times delta t, right? I times delta t charge is nothing but current into time, right? So what is the potential difference between A and B? Potential difference between A and B is, let's say this, let's call this as delta U. This is UB minus UA, which is again Q into VB minus VA, right? This is potential energy. And can I call this as minus Q into delta V? Why I have written minus here? Because VB is less than VA. Can I call this as minus Q delta V? Right. So this is the potential energy, decrease in potential energy when a charge carrier is moving from A to B. But if there is a decrease in potential energy, there is increase in some energy. You know, total energy will be constant. So kinetic energy, which is the major carrier after potential energy. So if potential energy goes down, kinetic energy will come up, right? So that net energy is zero and kinetic energy will be minus of delta U, which is Q times delta V. Q times delta V, this kinetic energy. And where this kinetic energy is going? We should know where this kinetic energy is going. So this kinetic energy results in the vibration of carriers, right? And it will result in dissipation of power or a heat. This will go as a heat energy in this conductor, right? If I write this charge, so this kinetic energy is, let's say, goes in terms of work, and this becomes Q into delta V is potential, and Q is nothing but I into delta T and into V, right? So this work done is dissipated as heat, right? So this is called heating effect of electric current. So this W by delta T, which is equal to V into I, product of potential into current, this is called power. This is called power, right? So power is V into I. And what about energy? Energy is V into I into T, which you can see. So let's say for a resistor, let's say for a resistor, sorry, not resistors. Let's say a resistor of resistance R carrying current I maintained through potential V, right? What is the power dissipated in this resistor? P equal to V into I. And you know V equal to IR, right? So P becomes what? I square R. P becomes what? I square R, right? And also it can be written as V square by R if you want to say in terms of V or I, right? So this much amount of power, or if I multiply it by time, it will get heat energy. So this energy is getting dissipated in this resistor. And where is this energy coming from? So only source which we have is cell or a battery or any power source which we have, right? So that cell's chemical energy, cell has chemical energy which is getting dissipated as heat energy here in this resistor, right? Okay. And this dissipation of heat energy is also called as ohmic loss. Ohmic loss, right? So let's understand how this equation is relevant in our day-to-day use case, right? So let's say you would have seen transmission line, right? You would have seen transmission line which brings power from a power plant to our homes, right? So there are a lot of networks in between, but just understand that power is generated somewhere, it is transmitted through some point and then it is distributed to our homes. This is how a network grid looks like. So if we have to, let's say there is a load is our home, right? If there is a load which needs a power P, a load which needs a power P, and it has a voltage V, right? A load which needs a power P and has a voltage V, and we need to feed this load from a transmission line, right? We need to feed this load. So how much current I need? I need a current P by V. This much amount of current I need, right? And I have a transmission line, right? This is a transmission line which has a resistance of RC, and this is my source. This is my source. So using this transmission line, see, we don't have power plants in every city, right? We don't have power plants in every city or town. We have power plants in some remote locations. Using transmission line, we supply our source to our load. So now to supply this load, I am using a transmission line in between, which is a conductor which will have resistance, and there will be a heat dissipated in that. How much is that heat? Heat will be I square into RC. RC is the resistance of this cable or a transmission line, right? I square into RC. So if current I need is P square by V square and resistance is RC, so this power is dissipated means consumed in transmission line, in transmission cable is P square by V square into RC. Now you see, this dissipated power is inversely proportional to voltage square. Now you see, to reduce this dissipation so that I can give maximum efficiency to homes, maximum voltage, maximum output to homes, I need to do this transmission at a higher voltage. If I do it at a higher voltage, I'll be dissipating less power, less energy, and I can have better efficiency. So you would have seen that transmission lines are written with danger 11 kV, some 33 kV like that. So intention of that high voltage 11,000 volt and things are to reduce the dissipation of power in transmission line, right? And so to better our efficiency. So now you can see how you can relate these equations to things happening in the practical life as well, right? So in next topic we'll discuss about combination of these resistors in series and parallel, and after that we'll discuss more topics on current, electricity, and solving a lot of numericals. Till then, thanks, best of luck.